Never revision mode.
Even if you don't know how to code, but you might want to learn the basics of programming in the meantime. In this course, we will be using the Python programming language. Python reads a lot like regular English, and is the language you will most likely encounter when learning about algorithms these days. If you don't know how to code, or if you know how to code in a different language, check out the notes section of this video for links to other content that might be useful to you. As long as you understand the fundamentals of programming, you should be able to follow along pretty well. If you're a JavaScript developer, or a student who's learning JavaScript, for example, chances are good that you'll still be able to understand the code we write later. I'll be sure to provide links along the way if you need anything to follow up on. Let's start with something simple. What is an algorithm? An algorithm is a set of steps or instructions for completing a task. This might sound like an oversimplification, but really that's precisely what an algorithm is. A recipe is an algorithm, your morning routine when you wake up is an algorithm, and the driving directions you follow to get to a destination is also an algorithm. In computer science, the term algorithm more specifically means the set of steps a program takes to finish a task. If you've written code before, any code really, generally speaking, you have written an algorithm. Given that much of the code we write can be considered an algorithm, what do people mean when they say you should know about algorithms? Now consider this.
The
Let's
past
say I'm a teacher in a classroom,
was
and I tell
everything.
everyone I have an assignment for them. On their desks, they have a picture of a maze, and their task is to come up with a way to find the quickest way out of the maze. Everyone does their thing and comes up with a solution. Every single one of these solutions is a viable solution, and is a valid example of an algorithm, the steps one needs to take to get out of the maze. But for being in classrooms, or any group of any sort, you know that some people will have better ideas than others. We all have a diverse array of skill sets. Over time, our class picks the best of these solutions, and anytime we want to solve a maze, we go with one of these solutions. This is what the field of algorithms is about. There are many problems in computer science, but some of them are pretty common regardless of what project you're working on. Different people have come up with different solutions to these common problems, and over time, the field of computer science has identified several that do the job well for a given task. When we talk of algorithms, we're referring to 2 points. We're primarily saying there's an established body of knowledge on how to solve particular problems well, and it's important to know what these solutions are. Now, why is it important? If you're unaware that a solution exists, you might try to come up with one yourself, and there's a likelihood that your solution will be as good or efficient, whatever that means, compared to those that have been thoroughly reviewed. But there's a second component to it as well. Part of understanding algorithms is not just knowing that an algorithm exists, but understanding when to apply it. Understanding when to apply an algorithm requires properly understanding the problem at hand. And this, arguably, is the most important part of learning about algorithms and data structures. As you progress through this content, you should be able to look at a problem and break it down into distinct steps. When you have a set of steps, you should then be able to identify which algorithm or data structure is best for the task at hand. This concept is called algorithmic thinking, and it's something we're going to try and cultivate together as we work through our content. Lastly, learning about algorithms gives you a deeper understanding about complexity and efficiency in programming. Having a better sense of how your code will perform in different situations is something that you will always want to develop and hone. Algorithmic thinking is why algorithms also come up in big tech interviews. Interviewers don't care as much that you are able to write a specific algorithm in code, but more about the fact that you can break a seemingly insurmountable problem into distinct components and identify the right tools to solve each distinct component. And that is what we plan on doing. In this course, though, we're going to focus on some of the tools and concepts you'll need to be aware of before we can dive into the topic of algorithms. If you're ready, let's get started. Hey again, in this video, we're going to do something unusual. We're going to play a game. And by we, I mean me and my two friends here, Brittany and John. This game is really simple, and you may have played it before. It goes something like this. I'm going to think of a number between 1 and 10, and they have to guess what the number is. Easy, right? When they guess a number, I'll tell them if their guess is too high or too low. The winner is the one with the fewest tries. Alright, John, let's start with you. I'm thinking of a number between 1 and 10. What is it? Between you and me, the answer is 3.
Quick question. Does the range include 1 and 10?
That is a really good question. So what John did right there was to establish the bounds of our problem. No solution works on every problem, and an important part of algorithmic thinking is to clearly define what the problem set is and clarify what values count as inputs. Yeah, 1 and 10 are both included.
Is it 1?
Too low.
Is it 2?
Too low.
Is it 3?
Correct. Okay, so that was an easy one. It took John 3 tries to get the answer. Let's switch over to Brittany and play another round using the same number as the answer. Okay, Brittany, I'm thinking of a number between 1 and 10 inclusive, so both 1 and 10 are in the range. What number am I thinking of?
Is it 5?
Too high.
2?
Too low.
Is it 3?
Correct. Alright, so what we had there was two very different ways of playing the same game. Somehow, with even such a simple game, we saw different approaches to figuring out a solution. To go back to algorithmic thinking for a second, this means that with any given problem, there's no one best solution. Instead, what we should try and figure out is what solution works better for the current problem. In this first pass at the game, they both took the same amount of turns to find the answer, so it's not obvious who has the better approach, and that's mostly because the game was easy. Let's try this one more time, and this time the answer is 10. Alright, John, you first.
Is it 1?
Too low.
Is it 2?
Still too low.
Is it 3?
Too low.
Is it 4?
Too low.
Is it 5?
Still too low.
Is it 6?
Too low.
Is it 7?
Too low.
Is it 8?
Too low.
Is it 9?
Too low.
Is it 10?
Correct. You got it. Okay, so now, same thing, but with Brittany this time.
Is it 5?
Too low.
8?
Too low.
Is it 9?
Still too low.
It's 10.
Alright, so here we start to see a difference between their strategies. When the answer was 3, they both took the same number of turns. This is important. When the number was larger, but not that much larger, 10 in this case, we start to see that Brittany's strategy did better. She took 4 tries while John took 10. We've played 2 rounds so far, and we've seen a different set of results based on the number they were looking for. If you look at John's way of doing things, then the answer being 10, the round we just played, is his worst case scenario. He will take the maximum number of turns, 10, to guess it. When we picked a random number, like 3, it was hard to differentiate which strategy was better because they both performed exactly the same. But in John's worst case scenario, a clear winner in terms of strategy emerges. In terms of algorithmic thinking, we're starting to get a sense that the specific value they're searching for may not matter as much as where that value lies in the range that they've been given. Identifying this helps us understand our problem better. Let's do this again for a range of numbers from 1 to 100. We'll start by picking 5 as an answer to trick them. Okay, so this time we're going to run through the exercise again, this time from 1 to 100, and both 1 and 100 are included.
Is it 1?
At this point, without even having to run through it, we can guess how many tries John is going to take. Since he starts at 1 and keeps going, he's going to take 5 tries as we're about to see.
Is it 5?
Cool, correct. Okay, now for Brittany's turn.
Is it 50?
Too high.
Is it 25?
Still too high.
Is it 13?
Too high.
Is it 7?
Too high.
Is it 4?
Too low.
Is it 6?
Too high.
Is it 5?
Correct. Let's evaluate. John took 5 tries. Brittany, on the other hand, took 7 tries. So John wins this round, but again, in determining whose strategy is preferred, there's no clear winner right now. What this tells us is that it's not particularly useful to look at the easy answers where we arrive at the number fairly quickly because it's at the start of the range. Instead, let's try one where we know John is going to do poorly. Let's look at his worst case scenario, where the answer is 100, and see how Brittany performs in such a scenario. Okay, John, let's do this one more time, 1 through 100 again.
Is it 1?
We can fast forward this scene because, well, we know what happens. John takes 100 tries. Alright, Brittany, you're up.
Is it 50?
Too low,
Is it 75?
too low,
88?
too low,
94?
too low,
Is it 97?
too low,
99?
too low.
100.
Okay, so that took Brittany 7 turns again, and this time she is the clear winner. If you compare their individual performances for the same number set, you'll see that Brittany's approach leaves John's in the dust. When the answer was 5, so right around the start of the range, John took 5 turns. But when the answer was 100, right at the end of the range, he took 100 tries. It took him 20 times the amount of tries to get that answer compared to Brittany. On the other hand, if you compare Brittany's efforts, when the number was 5, she took 7 tries. But when the number was 100, she took the same amount of tries. This is pretty impressive. If we pretend that the number of tries is the number of seconds it takes Brittany and John to run through their attempts, this is a good estimate for how fast their solutions are. Okay, we've done this a couple times, and Brittany and John are getting tired. Let's take a break. In the next video, we'll talk about the point of this exercise. In the last video, we ran through an exercise where I had some of my coworkers guess what number I was thinking. So what's the point of that exercise? You might be thinking, hey, I thought I was here to learn about algorithms. The exercise we just did was an example of a real-life situation you will run into when building websites, apps, and writing code. Both approaches taken by John and Brittany to find the number I was thinking of are examples of searching for a value. It might be weird to think that there's more than one way to search, but as you saw in the game, the speed at which the result was obtained differed between John and Brittany. Think about this problem from the perspective of a company like Facebook. At the time of this recording, Facebook has 2.19 billion active users. Let's say you're traveling in a different country and meet someone you want to add on Facebook. You go into the search bar and type out this person's name. If we simplify how the Facebook app works, it has to search across these 2.19 billion records and find the person you are looking for. The speed at which you find this person really matters. Imagine what kind of experience it would be if, when you search for a friend, Facebook put up a spinning activity indicator and said, come back in a couple hours. I don't think we'd use Facebook as much if that was the case. From the company's perspective, working on making search as fast as possible using different strategies really matters. Now, I said that the two strategies Brittany and John used were examples of search. More specifically, these are search algorithms. The strategy John took, where he started at the beginning of the ring and just counted one number after the other, is a type of search called linear search. It is also called sequential search, which is a better description of how it works, or even simple search, since it really is quite simple. But what makes his approach an algorithm as opposed to just looking for something? Remember, we said that an algorithm is a set of steps or instructions to complete a task. Linear search is a search algorithm, and we can define it like this. We start at the beginning of the list or the range of values. Then we compare the current value to the target. If the current value is the target value that we're looking for, we're done. If it's not, we'll move on sequentially to the next value in the list, and then repeat step 2. If we reach the end of the list, then the target value is not in the list. This definition has nothing to do with programming, and in fact, you can use it in the real world. For example, I could tell you to walk into a bookstore and find me a particular book. And one of the ways you could do it is using the linear search algorithm. You could start at the front of the bookstore and read the cover or the spine of every book to check that it matches the book that you're looking for. If it doesn't, you go to the next book and repeat until you find it or run out of books. What makes this an algorithm is the specificity of how it is defined. In contrast to just jumping into a problem and solving it as we go along, an algorithm follows a certain set of guidelines, and we use the same steps to solve the problem each time we face it. An important first step to defining the algorithm isn't the algorithm itself, but the problem we're trying to solve. Our first guideline is that an algorithm must have a clear problem statement. It's pretty hard to define an instruction set when you don't have a clear idea of what problem you're trying to
Llévanos
solve.
de tu mano, Pei.
In defining the problem, we need to specify how the input is defined and what the output looks like when the algorithm has done its job. For linear search, the input can be generally described as a series of values, and the output is a value matching the one we're looking for. Right now, we're trying to stay away from anything code-related, so this problem statement definition is pretty generic, but once we get to code, we can actually tighten this up. Once we have a problem, an algorithm is a set of steps that solves this problem. Given that, the next guideline is that an algorithm definition must contain a specific set of instructions in a particular order. We really need to be clear about the order in which these instructions are executed. Taking our simple definition of linear search, if I switch up the order and then move sequentially to the next value before specifying that first comparison step, if the first value were the target one, our algorithm wouldn't find it because we moved to the second value before comparing. Now you might think, okay, that's just an avoidable mistake, kind of common sense. The thing is, computers don't know any of that and just do exactly as we tell them, so a specific order is really important. The third guideline is that each step in our algorithm definition must not be a complex one and needs to be explicitly clear. What I mean by that is that you shouldn't be able to break down any of the steps into additional subtasks. Each step needs to be a distinct one. We can't define linear search as search until you find this value, because that can be interpreted in many ways and further broken down into many more steps. It's not clear. Next, and this one might seem obvious, but algorithms should produce a result. If it didn't, how would we know whether the algorithm works or not? To be able to verify that our algorithm works correctly, we need a result. Now, when using a search algorithm, the end result can actually be nothing, which indicates that the value wasn't found, but that's perfectly fine. There are several ways to represent nothing in code, and as long as the algorithm can produce some result, we can understand its behavior. The last guideline is that the algorithm should actually complete and cannot take an infinite amount of time. If we let John loose in the world's largest library and asked him to find a novel, we have no way of knowing whether he succeeded or not unless he came back to us with a result. Okay, so quick recap. What makes an algorithm and not just something you do? One, it needs to have a clearly defined problem statement, input, and output. When using linear search, the input needs to be just a series of values. But to actually use Brittany's strategy, there's one additional precondition, so to speak. If you think about her strategy, it requires that the numbers be sorted in ascending order. This means that where the input for John is just a series of values, to solve the problem, the input to Brittany's algorithm needs to be a sorted series of values. So, clearly defined problem statement, clearly defined input, and clearly defined output. Second, the steps in the algorithm need to be in a very specific order. The steps also need to be distinct. You should not be able to break it down into further subtasks. Next, the algorithm should produce a result. And finally, the algorithm should complete in a finite amount of time. These guidelines not only help us define what an algorithm is, but also helps us verify that the algorithm is correct. Executing the steps in an algorithm for a given input must result in the same output every time. If, in the game I played, the answer was 50 every time, then every single time, John must take 50 turns to find out that the answer is 50. If somehow he takes 50 turns in one round, then 30 the next, then we technically don't have a correct algorithm. Consistent results for the same set of values is how we know that the algorithm is correct. I should stress that we're not going to be designing any algorithms on our own, and we'll start off and spend most of our time learning the tried and true algorithms that are known to efficiently solve problems. The reason for talking about what makes for a good algorithm, though, is that the same set of guidelines makes for good algorithmic thinking, which is one of the most important skills we want to cultivate. When we encounter a problem, before rushing in and thinking about solutions, what we want to do is work through the guidelines. First, we break down the problem into any possible number of smaller problems where each problem can be clearly defined in terms of an input and an output. Now that we know how to generally define an algorithm, let's talk about what it means to have a good algorithm. An important thing to keep in mind is that there's no one single way to measure whether an algorithm is the right solution because it is all about context. Earlier, we touched on two concepts, correctness and efficiency. Let's define correctness more clearly because before we can evaluate an algorithm on efficiency, we need to ensure its correctness. Before we define our algorithms, we start by defining our problem. In the definition of that problem, we have a clearly defined input satisfying any preconditions and a clearly defined output. An algorithm is deemed correct if on every run of the algorithm against all possible values in the input data, we always get the output we expect. Part of correctness means that for any possible input, the algorithm should always terminate or end. If these two are not true, then our algorithm isn't correct. If you were to pick up an algorithms textbook and look up correctness, you will run into a bunch of mathematical theory. This is because traditionally, algorithm correctness is proved by mathematical induction, which is a form of reasoning used in mathematics to verify that a statement is correct. This approach involves writing what is called a specification and a correctness proof. We won't be going into that in this course. Proof through induction is an important part of designing algorithms, but we're confident that you can understand algorithms, both in terms of how and when to use them, without getting into the math. So if you pick up a textbook and feel daunted, don't worry, I do too, but we can still figure things out without it. Alright, so once we have a correct algorithm, we can start to talk about how efficient an algorithm is. Remember that this efficiency ultimately matters because they help us solve problems faster and deliver a better end-user experience in a variety of fields. For example, algorithms are used in the sequencing of DNA, and more efficient sequencing algorithms allow us to research and understand diseases better and faster. But let's not get ahead of ourselves. We'll start simple by evaluating John's linear search algorithm in terms of its efficiency. First, what do we mean by efficiency? There are two measures of efficiency when it comes to algorithms, time and space. Sounds really cool and very sci-fi, huh? Efficiency measured by time, something you'll hear called time complexity, is a measure of how long it takes the algorithm to run. Time complexity can be understood generally outside the context of code and computers because how long it takes to complete a job is a universal measure of efficiency. The less time you take, the more efficient you are. The second measure of efficiency is called space complexity, and this is pretty computer specific. It deals with the amount of memory taken up on the computer. Good algorithms need to balance between these two measures to be useful. For example, you can have a blazingly fast algorithm, but it might not matter if the algorithm consumes more memory than you have available. Both of these concepts, time and space complexity, are measured using the same metric, but it is a very technical sounding metric, so let's build up to it slowly and start simple. A few videos ago, I played a game with Brittany and John where they tried to guess the number I was thinking. Effectively, they were searching for a value. So how do we figure out how efficient each algorithm is and which algorithm was more suited to our purposes? If we consider the number of tries they took to guess or search for the value as an indicator of the time they take to run through the exercise, this is a good indicator of how long the algorithm runs for a given set of values. This measurement is called the running time of an algorithm, and we'll use it to define time complexity. In the game, we played 4 rounds. Let's recap those here, focusing on John's performance. In round 1, we had 10 values, the target was 3, and John took 3 turns. In round 2, we had 10 values, the target was 10, and John took 10 turns. In round 3, we had 100 values, the target was 5, John took 5 tries. And finally, in round 4, when the target was 100, given 100 values, John took 100 tries. On paper, it's hard to gauge anything about this performance. When it comes to anything with numbers, though, I like to put it up on a graph and compare visually. On the vertical, or y-axis, let's measure the number of tries it took John to guess the answer, or the running time of the algorithm. On the horizontal, or x-axis, what do we put? For each turn, we have a number of values as well as a target value. We can plot the target value on the horizontal axis but that leaves some context and meaning behind. It's far more impressive that John took 5 tries when the range went up to 100 than when he took 3 tries for a maximum of 10 values. We could plot the maximum range of values, but then we're leaving out the other half of the picture. There are data points, however, that satisfy both requirements. If we only plot the values where the target, the number John was looking for, was the same as the maximum range of values, we have a data point that includes both the size of the dataset as well as his effort. There's an additional benefit to this approach as well. There are 3 ways we can measure how well John does, or in general, how well any algorithm does. First, we can check how well John does in the best case or good scenarios from the perspective of his strategy. In the range of 100 values, the answer being a low number, like 3 at the start of the range, is a good scenario. He can guess it fairly quickly. 1 is his best case scenario. Or we could check how well he does on average. We could run this game a bunch of times and average out the running time. This would give us a much better picture of John's performance over time, but our estimates would be too high if the value he was searching for was at the start of the range, or far too low if it was at the end of the range. Let's imagine a scenario where Facebook naively implements linear search when finding friends. They looked at the latest US Census, saw that 50% of names start with the letters A through J, which is the first 40% of the alphabet, and thought, okay, on average, linear search serves us well. But what about the rest of those whose names start with a letter after J in the alphabet? Searching for my name would take longer than the average, and much longer for someone whose name starts with the letter Z. So while measuring the runtime of an algorithm on average might seem like a good strategy, it won't necessarily provide an accurate picture. By picking the maximum of the range, we're measuring how our algorithm does in the worst case scenario. Analyzing the worst case scenario is quite useful because it indicates that the algorithm will never perform worse than we expect. There's no room for surprises. Back to our graph, we're going to plot the number of tries, a proxy for running time of the algorithm, against the number of values in the range, which will shorten to n. N here also represents John's worst case scenario. When n is 10, he takes 10 turns. When n is 100, he takes 100 turns. But these 2 values alone are insufficient to really get any sort of visual understanding. Moreover, it's not realistic. John may take a long time to work through 100 numbers, but a computer can do that in no time. To evaluate the performance of linear search in the context of a computer, we should probably throw some harder and larger ranges of values at it. The nice thing is by evaluating a worst case scenario, we don't actually have to do that work. We know what the result will be. For a given value of n, using linear search, we will take n tries to find the value in the worst case scenario. So let's add a few values in here to build out this graph. Okay, so we have a good picture of what this is starting to look like. As the values get really large, the running time of the algorithm gets large as well. Well, we sort of already knew that. Before we dig into this runtime any deeper, let's switch tracks and evaluate Brittany's work. By having something to compare against, it should become easier to build a mental model around time complexity. The algorithm John used, linear search, seemed familiar to us, and you could understand it because it's how most of us search for things in real life anyway. Brittany's approach, on the other hand, got results quickly, but it was a bit harder to understand, so let's break it down. Just like John's approach, Brittany started with a series of values or a list of numbers as her input. Where John just started at the beginning of the list and searched sequentially, Brittany's strategy is to always start in the middle of the range. From there, she asks a comparison question. Is the number in the middle of the range equal to the answer she's looking for? And if it's not, is it greater than or less than the answer? If it's greater than, she can eliminate all the values less than the one she's currently evaluating. If it's lesser than the answer, she can eliminate all the values greater than the one she's currently evaluating. With the range of values that she's left over with, she repeats this process until she arrives at the answer. Let's visualize how she did this by looking at round 3. In round 3, the number of values in the range was 100. The answer was 5. The bar here represents the range of values, 1 at the left, 100 at the right, and this pointer represents the value Brittany chooses to evaluate. So she starts in the middle at 50. She asks, Is it equal to the answer? I say it's too high. So this tells her that the value she is evaluating is greater than our target value, which means there's no point in searching any of the values to the right of 50. That is, values greater than 50 in this range, so she can discard those values altogether. She only has to consider values from 1 to 50 now. The beauty of this strategy, and the reason why Brittany was able to find the answer in such few turns, is that with every value she evaluates, she can discard half of the current range. On her second turn, she picks the value in the middle of the current range, which is 25. She asks the same question. I say that the value is too high again, and this tells her that she can discard everything greater than 25, and the range of values drops from 1 to 25. Again, she evaluates the number in the middle, roughly, so that'd be 13 here. I tell her this is still too high. She discards the values greater, moves to value 7, which is still too high. Then she moves to 4, which is now too low. She can discard everything less than 4, which leaves the numbers 4 through 7. Here she picked 6, which was too high, which only leaves one value, 5. This seems like a lot of work, but being able to get rid of half the values with each turn is what makes this algorithm much more efficient. Now there's one subtlety to using binary search, and you might have caught on to this. For this search method to work, as we've mentioned, the values need to be sorted. With linear search, it doesn't matter if the values are sorted. Since a linear search algorithm just progresses sequentially, checking every element in the list, if the target value exists in the list, it will be found. But let's say this range of values 1 to 100 was unsorted. Brittany would start at the middle with something like 14 and ask if this value was too low or too high. I say it's too high, so she discards everything less than 14. Now, this example starts to fall apart here because, well, Brittany knows what numbers are less than 14 and greater than 1. She doesn't need an actual range of values to solve this. The computer, however, does need that. Remember, search algorithms are run against lists containing all sorts of data. It's not always just a range of values containing numbers. In a real use case of binary search, which we're going to implement in a bit, the algorithm wouldn't return the target value because we already know that. It's a search algorithm, so we're providing something to search for. Instead, what it returns is the position in the list that the target occupies. Without the list being sorted, a binary search algorithm would discard all the values to the left of 14, which over here could include the position where our target value is. Eventually, we'd get a result back saying the target value doesn't exist in the list, which is inaccurate. Earlier, when defining linear, simple search, I said that the input was a list of values and the output was the target value, or more specifically, the position of the target value in the list. With binary search, there's also that condition, the input list must be sorted. So let's formally define binary search. First, the input, a sorted list of values. The output, the position in the list of the target value we're searching for, or some sort of values indicate that the target does not exist in the list. Remember our guidelines for defining an algorithm? Let me put those up again really quick. The steps in the algorithm need to be in a specific order. The steps also need to be very distinct. The algorithms should produce a result. And finally, the algorithm should complete in a finite amount of time. Let's use those to define this algorithm. Step 1, we determine the middle position of the sorted list.
¿Qué tal?
Step 2, we compare the element in the middle position to the target element.
¿Por qué bien?
Step
Sí,
3,
sí, sí, sí.
if the elements match, we return the middle position and end.
Cuando
If they don't
15
match,
minutos.
in step 4, we check
¿Por qué
whether
se
the
te
element in the middle position
Faltan dos
is
partidos.
smaller than the target
¿Qué
element.
tal?
If it is, then we
Ay,
go
bájale
back
de una
to
vez,
step
está
2
contento de
with a
ver.
new list that goes from the middle position of the
Empezaron a
current
llegar
list
el
to the
montón
end
de...
of the current list.
No sé
In
por
step
qué
5,
suena.
if the element in the middle position is greater than the target element, then again we go back to step 2 with a new list that goes from the start of the current list to the middle position of the current list. We repeat this process until the target element is found, or until a sublist contains only one element.
¿Qué tal?
Bien.
¿Sin novedad? ¿Por qué viene doliendo trago?
No vengo oliendo otra vez, es mentira. Tendrá mal aliento, olor a café, qué sé yo, pero... Tengo que salir de ahí del estacionamiento de Guy entrar no es tan difícil, salir es una mierda.
Así.
Es súper angosto la salida.
Y un ratón ahí.
Claro, te lo echo para adelante, echo para atrás. Ahora mira cómo me quedaron hermosos.
Uy, y echaste pica del teléfono.
Ah,
Y
ya
tu
me
gran
dijeron.
suerte. ¿Ya le entregaron?
Sí.
¿Y qué dice? Yo te mandé un fotito.
Estaba mi mamá como
Ay,
que,
ay.
hija, necesito que me colabore con medicamentos, necesito ir a comprar unos atamel, un tachipirín, una vaina porque se preocupa que se le baje esa fiebre que tiene.
Ah, estaba contento.
Claro, me imagino.
Un juguete nuevo.
Sí, ya, a ver. Vamos. Pero, porque casi que todos los semáforos en verde,
¿Por dónde venís?
por la prensa.
Por la prensa.
Ajá. Y me ha
Pero esta hora es.
es vota, es que ese es el problema, que es votado, ¿no?
Claro.
Pero me dieron el Santa María, porque ahí que agarró el semáforo en rojo.
¿Y qué comí? Bueno, ya baja y ahora hablamos.
Estamos ocupados.
No, porque el chiqui te está esperando. Verga. Trini. Chiqui. ¿Se encontraron con alguien?
¿No? O bueno, cuando llegamos abajo estaba un chico con Rico, pero como que nos vio y ya se fue.
Unos runeros.
Ajá.
Ah, buena onda el muchacho. Creo que es medio más grandes que la chiqui los dos.
Sí, son grandes.
Blanquita y café.
Y uno café, ajá. Ya el chico como
Súper
que
respeto y buena onda el muchacho.
nos vio y como que ya se retiró él. Entonces ahí chiqui ya se
Tranquilo.
vino, hizo tremenda cagada de 3 mojones.
¿Y qué te iba a decir? ¿Qué tal? ¿Fueron al súper? ¿Qué comiste?
Bueno, yo fui hasta el bosque y Gaby me estaba esperando en el bosque.
Ya.
Lo mismo, Gaby no había comido donde Quiqueja.
Ah, vinieron hasta acá. Y no me viniste a ver.
Ahí en el bosque.
Ah, en el bosque de Quiqueja.
Ajá. Y ahí comimos.
Y sí fue lo mismo.
Me parece un poco más rico el de aquí. Pero estaba muy bueno.
¿Qué pediste? ¿Lo mismo?
El mismo. El pedimos lo mismo.
Ah, las dos pidieron lo mismo. ¿Qué agrias? Bueno, cada uno, cada uno.
Ella va chiquita. Y de ahí.
Yo sí estaba confiando en que al rato viene mi esposa con ese choripán que le dije. Bueno, y fueron al súper, hicieron las compras.
Bueno, primero estábamos en el súper, después dejamos las cosas en el carro y fuimos a comer. Llegamos casi que a las 3:30, casi 4 donde Gaby. Mientras se bajaba, no me estacionaba. Bajaba todas las cosas, bajamos, hicimos 2 viajes, bajando todo. Ya, mientras ella.
Ah, compró full.
Bueno, o sea, no más o menos, pero eran sus cosas y mis cosas.
¿Y qué compraste tú?
O sea, no, los materiales.
Ah, ya.
Y de ahí, ya no compré nada. Y de ahí, después nos fuimos a que es el café.
¿Dónde
Y
fueron el
empezó a
café?
lavar. No, ahí mismo, que Gaby se lo café.
Ah, ya.
Empezamos a hacer, pero que si parándose y no sé qué, ya se nos hizo tarde. Una uña me salió fea, tuve que quitar.
Creo que otra vez he escuchado que tu mamá sabe decir eso de, uy, que hay que comprar medicina por cuando alguien se pone muy contento o algo así. Porque les da como que da fiebre.
Pero me lo dijo en serio que yo me asusté.
Ajá.
Mañana hay paro nacional.
Ah, sí. ¿De quién? ¿El Frente Unitario de Trabajadores, de Indios y Transportistas?
Dice por precios de productos y combustible.
Pero sí, el detergente está más barato que nunca. Y el papel se consigue por toneladas. Paro nacional. ¿Qué dirán mis amigos de Beso Negro Periodismo? Uy, qué nombre más tonto. Uy,
¿Qué?
si yo pensaba hacer un proyecto serio, era que ya le cambien. ¿Qué? Verga. Beso Negro Periodismo. Periodismo. ¿Y pasearon en el bosque chance?
No.
¿Y por qué el super maxi del bosque?
Porque
Ah, le queda cerca de la iglesia, ¿no?
le queda cerca de la iglesia. y mi amiga me responde que bueno, que ese trámite no es como que lo están haciendo mucho porque está paralizado, pero como que me ayuda por $380. Algo. Mucho dinero.
Mucha plata.
Para que
Pero ¿y
me
qué?
llegue
¿Y
el
no hay
tipo
esperanza en que
mañana.
por la vía normal llegue?
No sé, vamos a esperar a ver qué me dice el otro chico mañana, porque primero como que me van a revisar a ver en qué estatus está.
Porque... a veces como que... Uy, ni sabe. Qué hueva. Chiqui Coneja. ¿Y por qué Chiqui Coneja no sale en esa foto?
¿Quién fue?
Esa que pusiste el estado.
No sé.
Pero sí estaba presente, ¿no?
Sí.
Entonces, parece el espaldar de un lugar. Ah, es como de una hamburguesería, algo así, ¿no?
No me acuerdo.
El espaldar del Tantra.